Morning everyone. So in today's lecture we'll discuss about potential due to infinite line charge, a charged ring, and we'll also discuss about energy density, right? So in the previous lecture we'll just recap what we discussed in the previous class. So we discussed about work done and we considered one point, from in the presence of charge, if we move a charge from point A to point B, what will be the work done? So that we have discussed in the previous lecture. And then we also discussed about the potential difference. Just by cross multiplying the charge we get what is the work done per unit charge. So that is the potential difference in moving the charge from A to B, and then this is absolute potential or potential at that particular point, right? So when we consider the second point is at infinity, right? Then when we measure the potential difference between a given point and the point where v is 0, v will be 0 only when the length is at when the length is infinity, right? When the distance is infinity. So that will give you the potential. And then we have also seen that what is the potential when the charge is not at the origin, right? We have to obtain the position vector of both the charge and the point where we have to calculate the potential, and then we have to apply the potential formula, this formula, right? And also we have seen Maxwell's equations, that is the relationship between E vector and V vector, E vector and V, where E vector is electric field intensity, and V is the potential, right? So now we'll just see what are the formulas or what all we have derived in the last class. So now this was the equation for, sorry, this was the equation for work done, right? This was the equation for the work done. This was the equation for the work done, right? And the same thing when we divide this q, when we cross multiply with this q here, we get the potential difference. And then this is absolute potential or potential, and this is the potential of r when the charge is not at the origin, right? And we have seen two equations for Maxwell, that is in integral form and differential form. So that is over the closed length closed loop, E vector dot dl vector will be 0 and the curl of E vector will be 0. So these two are very important, right? And at last we have seen that the electric field intensity is the negative gradient of V. So these are the things what we discussed in the previous lecture, right? So now we'll move on to today's lecture. So first we'll discuss what is the potential due to the infinite line charge. So previously we have discussed what is electric field intensity due to infinite line charge, and in the application of Gauss law also we have discussed what is the electric field intensity or electric flux density due to infinite line charge. So now we are discussing what is the potential difference due to the infinite line charge, right? So we consider this one where here we have an infinite line charge placed in this z-axis, the same thing whatever we have discussed for Gauss law and electric field intensity, right? Now there is a what to say, there's an infinite line, a charge placed on z-axis as shown here. Now what we are going to do is we are moving one charge from point B to point A in the presence of this infinite line charge. So we are trying to move this point B, we are trying to move the charge from point B to point A in the presence of this this infinite line charge, right? So we'll assume that the distance between the line and this point A is RA, and the distance between the line and this point B is RB. So RA and RB. And here what importantly you have to remember is this RA and RB are the perpendicular distances from this line charge and these 2 points, right? So this 2 points, whatever distances are mentioned, that is RA and RB. So these are, this RA and RB are the perpendicular distances from the infinite line charge, right? So this is one thing which you have, which you should note. Yeah. Now we know that the potential or the electric field intensity due to infinite line charge is given by this equation. And in the class, whatever we discussed, instead of this R, we had rho. So both are one and the same. Different textbooks use different notations here. So you just take this R as rho, right, and this AR as a rho, right? Or you can keep it as it is. But you should note that this is in cylindrical coordinate system. Whatever you are doing now is in cylindrical coordinate system, right? Now we know this equation in this from the second module, that is E vector is equal to rho L divided by 2 pi epsilon naught R into AR cap. Now DL, coming to DL in cylindrical coordinate system, DL is equal to d rho A rho cap plus whatever we have. Now here, as I told you, since we are taking this as the perpendicular distance, we are concerned only with the radial component, that is AR. The other one, A phi and AZ, are not required, right? So DL will have only one component of AR cap or A rho cap, that you have to remember here. Now, yes, now here we are deriving the equation for potential difference, right? So potential difference is given by, we have seen that in the previous slide. So this is the equation for potential difference which we derived yesterday, right? So the same equation is applied here. So VAB is equal to minus B to A E vector dot DL vector. So here the point is moved from B to A. That is why we have here B to A, right? And this negative sign is because when we are moving the charge from point B to point A in the presence of this electric field or infinite line charge, the external source has to do the work. That is why we have this negative sign, right? Now this is the formula. Now we know what is E vector and we know what is DL vector. So just substitute those two. So when we are substituting those two, what do we get here? R, B is nothing but, here we have R, just write it, it is not shown here, RB to RA. And E vector is nothing but rho L divided by 2 pi epsilon naught R into AR cap, and DL vector is nothing but dr into AR cap from these two equations, right? So this is E vector and this is DL vector, right? This is DL vector. So just we have to find the dot product of those two. Now coming to the next slide. So solving this equation, what happens is, now we have dot product and we have AR and AR. AR dot AR will be 1, which you know. So now what we get is rho L divided by 2 pi epsilon naught R into dr. Now it is clear that we have to do the integration with respect to R. So R varies from RB to, here we have R. It is not clear here. So here also we have R. So RB to RA minus rho L by 2 pi epsilon naught into 1 by R. So that is this R, right? Now coming to the next slide. So just solve this one. So we know that the integration of 1 by R is L natural logarithmic of R. So when you solve this one, you will get minus rho L divided by 2 pi epsilon naught ln of RA minus ln of RB. So to eliminate this negative sign, we can write it as ln of RB minus ln of RA, which is nothing but ln of RB by RA. So the difference of logarithmic functions can be written as division, which you know. So this formula you have to remember. So this is the potential difference between point A and B. That is VAB is given by rho L, where rho L is the charge density of this line divided by 2 pi epsilon naught natural logarithmic of RB, which is this is RB divided by RA. So this is the derivation for potential difference due to infinite line charge. So we'll move on to the next one. Now next one, potential at a point due to a circular ring, right? So now just understand this diagram first, then we'll go to the derivation. Now here whatever ring we have, this particular ring, right? This is a charged ring. So we cannot consider the whole length for the analysis. So we'll consider only this DL part. So we'll consider a segment of DL. We'll consider only a small segment of this DL, right? Now what will be the length of this DL if you consider cylindrical coordinate system? Now if I draw a line like this, so we know that this angle will take it as d phi. This we know when we discuss differential elements. So this angle will take it as d phi, right? When this angle is d phi, what will be this length dl? This dl length will be the radius of this line, the radius of this ring we have taken as a. So it will be a d phi, right? A d phi. And what will be the unit vector of this one? So the unit vector will be like this, so which is nothing but a phi. It will be a phi cap. So this is dl vector. I hope it is clear, right? Now, yes. Now what we are trying to do is, we have a charged circular ring here and we are obtaining what is the potential at this point A. So when we have to obtain the potential at point A, we need to know two things. One is due to this differential length, what is the length between this differential length and the point where we are calculating the potential. And the second thing is, we should know what is the perpendicular distance from the origin or the center of the ring to the point where we are calculating. So that is given by z. We are taking the point on z axis. So z is nothing but the distance between the center of the ring to the point where we are calculating the potential. And this capital R is equal to Pythagoras theorem, root of this a square plus z square. So we know what is the exact distance now between this differential length and this point A, right? So now we know that the potential is given by, this is not potential difference, it is potential, right? Potential is given by Q divided by 4 pi epsilon naught R, right? And what is R here? This R is nothing but the distance between the point and the charge. So now here we have taken it as capital R. So this small r is written as capital R here, and differentiating on both the sides, we get this as dVA. This is the equation what we get, right? dV by dQ by 4 pi epsilon naught R. Now dQ. Now we know that rho L is equal to dQ by dl. So now what will be dq? Dq will be rho L into, so dq will be rho L into dl. So that is what is written here, right? Now moving on to the next one, next line. So R, we know that R capital R is a square plus z square. So that is what is written here. Then substituting R in this equation and rho L for this, we get this equation, right? So here we can see that rho L a d phi. So this is for dl. So this a d phi is nothing but dl, right? Now solving this, now what is the limit of, what is the variable of integration here? D phi. So we know that phi varies from, here we have taken a small segment here, but this segment varies from 0 to 2 pi. So this covers the full circular ring. So we have to take the limits from phi is equal to 0 to 2 pi, and whatever is there here, the same thing is written here. So we have to integrate this. So only d phi is there, so it will be 2 pi to 0, so it will be 2 pi. So this will be 2 pi times the equation. So this is what we get here. So this is the potential at point A. This is the potential at point A due to the circular ring placed at the perpendicular height of Z, right? And with the radius of A. So rho L into A divided by 2 epsilon naught root of A square plus Z square. So this is the derivation for potential due to, potential at a point due to a charged circular ring, right? I hope it is clear. Now moving on to the next topic. So whatever we have discussed here is one part of the module, that is work done, potential and potential difference, and also that E is equal to negative gradient of V, right? So the next one, energy density in electrostatic fields. So now here we'll consider one diagram here. So please understand this diagram here. So now here what happens is, we have some region here, we have some space here which is free of charge initially, so I'll draw it here. So it will be like this first, right? There will be no charges like this before, right? Now this is free of charge, this region is free of charge. There will be nothing here in the beginning. So now what we'll be doing is, at some point, from some point infinity, we'll first bring q1 inside this space to point p1. So first we'll bring a charge of q1 to this point p1, right? Next what we'll do, now what will be the energy spent, or what will be the work done in getting this q1 from infinity to this point charge? It will be 0, because initially this region is free of charge, right? So there is no work done in getting q1 from infinity to this point p1. Now next what we'll do, from infinity we'll get one more charge to point p2, that is q2. So bringing q2 from infinity to point p2. Now what will be the work done? There has to be some work done, because already there is some charge q1, right? Now q2 depends on what is the charge q1, right? Now next again we'll consider one more charge from infinity, that is q3, which is brought to point p3. So here what you have to understand is, initially there was no charge in this region. First thing is, we will get charge q1 from infinity to this point p1, so no energy will be spent or no work will be done to get q1 from infinity to point p1. And next we'll get q2 from infinity to point P2. Now while getting Q2, there should be some energy spent because already there is some charge present Q1 which might be opposing this Q2, right? So there should be some energy spent. Next, while getting Q3 to this point P3 from infinity, getting Q3 from infinity, we have to do more work because there are already two charges here. So in the presence of these two charges, we are getting the third charge. So these two charges might oppose this third charge, right? So the work done will be different. Now we'll see what are the equations. Yes. So the work done will be equal to W1 plus W2 plus W3. So this is the work done in getting Q1, work done in getting Q2, and this is the work done in getting Q3, right? As I told you, work done in getting Q1 will be 0. Work done in getting Q2, you have to note here, work done in getting Q2 to point P2 will be equal to the charge Q2, and the potential difference between 1 and 2. Potential difference between 1 and 2. So that is what is written here. Now next, when we get charge Q3, so it will be work done will be Q3 into the potential difference between, already this charge was there, so the potential difference between 1 and 3 should be considered, and the Q2 also is there now, so we have to consider the potential difference between 2 and 3 also. So that is what is written here, V31 and V32. Suppose if we write Q4, how will we write? It will be plus Q4 into V41 plus V42 plus V43, right? I hope you understood. Now again the same equation. Now here, what is this equation? Now suppose if I interchange, I'll get Q3 first instead of Q1. If I get Q3 first instead of Q1, the work done will be 0, right? I'm reversing the order here. First we bought W1 here, Q1 first, Q2 second, and Q3 third. But in this equation, I'm interchanging the order. So first I'll get Q3, so there will be no charges. So the work done in getting the charge Q3 will be 0. Next is, when you get the second charge Q2, there will be already the third charge, so we have to consider Q2 into the potential difference between these two charges. And then while getting Q1, we have to consider the potential difference between these two charges and these two charges. So that is the equation. So this is when we get Q1, Q2, Q3 in order, and this is when we get Q3, Q2 and Q1 in order. So these two equations you have to note here. Now coming to the next slide. Coming to the next one. When we add both the equations, so when we add these two equations, that is WE is equal to 0 plus whatever equation is here, and WE is equal to whatever equation we have here. So when we add these two equations, here also we have WE and here also we have WE. So it's better if you have a paper and pen or book and pen, you just write down these two equations and add these two. So when I add these two equations, this will be 2 times WE is equal to Q2 into V21 plus V23 and so on. So that is this equation. So when you add those two equations, you will get this, that is Q1 V1 plus Q2 V2 plus Q3 V3, right? Now yes, so now WE will be half of Q1 V1 plus Q2 V2 plus Q3 V3. So this will be WE is equal to half of K is equal to 1 to N QK into VK, right? This formula can be used for n number of charges. Here we had used only 3 for analysis. So if there are n number of charges, this is a formula what you have to use, right? Similarly, for what is WE for line charge, surface charge and volume charge. So here this Vk or V will be the same here, that is V and V. So what is left? Q, right? How do you write Q for this thing rho L? So rho L is Q divided by or dq divided by dl, right? Or q is equal to integral of rho L into dl. So that is how you get this. That is how you get this rho L and dl. Similarly for rho S and ds and rho V and dV. These are just from the definitions of line charge density, surface charge density and volume charge density, right? So now yes, going to the next one. From this equation, now what I have done is I have taken this equation for the next topic, that is volume charge density. When I take this equation, that is the same thing I'm writing here. W is equal to half of rho V into dV. This V is potential. Don't get confused with respect to the volume. And this is volume differentiation, and this is the volume integral. So now in electrostatics we know that rho V is equal to divergence of d vector. Rho v is equal to divergence of d vector. So this rho v, I'm substituting it as divergence of d vector. Next, we have a formula here. When you have divergence of a vector into a scalar, we can write it as divergence of scalar into vector minus vector into gradient of v. Gradient of v. So substituting this formula here. So what I have done here, in place of this, I'm substituting this equation, right? Wherever capital A is there, that means it is D. So what we'll get, half of volume integral of divergence of this, that is scalar into vector into dv, minus this one, half of again volume integral of vector here A, but we are applying for D, into gradient of V into dV. So we are just applying this formula here. So by applying divergence theorem, I hope you remember divergence theorem from the second module. So divergence theorem, what does it say? So we can apply it here. That is volume integral of divergence of d vector into dv can be written as surface integral of d vector dot ds vector. We have solved many problems based on this, right? So now applying this divergence theorem, divergence theorem for this part, this is the equation, this is the equation for divergence theorem or formula for divergence theorem. So when we apply this, this is what we get. So for this part, divergence theorem is applied. And this is written as it is. Right? Before going to the next thing, you have to know a few things here. Now this is V, that is potential. When you take the radius, it varies as 1 divided by R, or potential is inversely proportional to R. And for D, it will be 1 divided by R cube. 1 divided by R cube. Now, and this ds is nothing but multiplication of two length into breadth. So if it is r, and this varies as r square, right? Now when you multiply all these three, what do we get? We get 1 by r, and 1 by r cube is multiplied, so we will get 1 by r power 4, and we have 1 by r square here. So the resultant will be r square. So here, when r tends to infinity, Now we get 1 by r square, sorry. We get 1 by r square. So here when r tends to infinity, this whole part becomes 0. When r tends to infinity, this whole part will become 0. So only this equation will be there. So that is what is written here. The same equation I've written again. So now this part will be 0 as r tends to infinity, because v is inversely proportional to 1 by v is inversely proportional to r, d is inversely proportional to r cube, and s is directly proportional to r square. So when you multiply all these, you will get 1 by r square. So when r tends to infinity, this becomes 0. So we are ignoring that. So we are writing only this equation. So now here, how did we write this? Now note here, we have one negative sign and we have gradient of v. So what was E? E was negative gradient of v. So this negative combined with this gradient of v, we can write it as E vector, right? So dv is as it is written here. D is also as it is written here, right? But this negative and this gradient of v combinedly, we are writing it as electric field intensity E, right? Now going to the next equation, that's what is given here. Now, yes, now WE, the same equation is written here. So we know that D is epsilon naught E. When you substitute for D here, you get epsilon naught into E square, and it's a dot product. So dot product of two vectors will be a scalar. So this will be 1 by 2 volume integral of epsilon naught E square into dV. So this is the equation for electrostatic energy, right? So now differentiating this on both the sides, if I want to eliminate this integration, I'll take this as small we is equal to dwe by dv, which is equal to 1 by 2 d into e, and this integration will go off because we have taken the differentiation here, which is equal to 1 divided by 2 epsilon naught e square. The same equation will be here without integration. And if you want this equation only with respect to d, then this is the equation, d square by 2 epsilon naught, by using this relation, right? So we can write it as closed integral of, not closed integral, volume integral of we into dv. So this is the theory part of this module. Now we'll go and we'll solve some problems based on whatever we have discussed, right? So this is the first problem. Please read this one. So there are 2 point charges. Minus 4 microcoulomb and 5 microcoulomb, and they are located at, that is 4 microcoulomb is located at 2 minus 1 3, and 5 microcoulomb is located at 4 4 0 4 and minus 2 respectively. So we have to find the potential at 1 0 1, assuming 0 potential at infinity. So when you see this 0 potential at infinity, that means we have to calculate the potential, not the potential difference, right? So roughly if you draw the diagram here, what do you get? How to draw the diagram here? Now there are two charges. This is one and this is the other one, right? Now the first charge is minus 4 microcoulomb. The second charge is 5 microcoulomb, right? And also now, because of these two charges, you have to calculate the potential at this point, some point here, that is 1 0 1, and minus 4 coulomb is located at 2 minus 1 3, right? And this 5 microcoulomb is located at 0, 4, minus 2. Now we have to calculate what is the potential at this point, like this and like this, right? Suppose you consider this as the first one, or A or B, whatever it is, and this as the second one. Now how do you calculate the distance between this 4 microcoulomb and this point? So it will be final minus initial, so it will be 1, 0, 1, minus 2, minus 1, 3. So this will be the first distance, and the second distance will be 0, sorry, final minus initial, right? Yes. Now for the second point, for 5 microcoulomb, it will be 1, 0, 1, minus 0, 4, minus 2. So calculate the distances, this distance and this distance. So we'll get some number. So then just apply in the formula. So we'll see what is there. I'll just erase this one. Yes, so this is the formula. Yeah, now here we can see final minus initial. This is what we had written. So we'll get root 6 for the first case and root 26 for the second case. So we know Q1 is 4 microcoulomb and Q2 is 5 microcoulomb. Just substitute it, and 1 by 4 pi epsilon naught, you can take it as constant here, right? So just substitute it, you will get minus 5.872 kilovolts, right? So what is the variable here in the formula? Just note that one, just to solve these kind of problems. Now what is the way, what just go through this formula once. So if you go through this formula, first you have to see what is known and what is unknown, right? So Q1 is given and Q2 is given. Anyway, 4 pi epsilon naught is a constant, and here also it is a constant. So we just need to know what is R minus R1 and R minus R2, right? So if you calculate these two, then it means that you have solved the problem. Just substitute it and get the answer. So that is why whenever you have a problem, just see what is known and what is unknown, and just see how you can approach to calculate the unknown, substitute it, and then get the answer. So this is the potential at 101, right? So we'll go to the next problem. Yes, just go through this problem. A point charge at 5 nanocoulomb is located at minus 340, while the line y is equal to 1 and z is equal to 1 carries uniform charge of 2 nanocoulomb, right? So before reading the subdivisions, just read this once more. So how many charges are there? There are two charges. One is a point charge and the other one is a line charge. So once you identify the type of charges, we need to know what is where is its location. Now if we draw, this is a rough sketch. So if you draw x, y and z, x, y and z. Now here a point charge of 5 nanocoulomb is located at minus 340, right? So first thing is minus 340 means for point charge we'll consider some point here. For point charge we'll consider some point, so that is minus 340. So this is for the point charge. Already for the point charge we have solved the problem in the previous problem, so it should not be a problem for calculating the distance between a given point and the point charge, given point and point charge. Now we'll see how to obtain the length between the given point and, or first we'll plot this infinite line charge. How does it look, right? So now we'll erase this one. So I'm not considering point charge as of now, because you know how to calculate the distance between the given point and the charge, point charge. Now, so the infinite line charge, you can see y is equal to 1 and z is equal to 1. So if this is y is equal to 1 and this is z is equal to 1, the line is placed in this manner. The line is placed in this manner, that is like this. It is placed like this from plus infinity to minus infinity. Now I told you in class, whenever you get the infinite line problems like this, now this is placed parallel to x-axis. So we have to ignore x-axis and look this particular diagram from this direction. You have to look it from this direction. When you look this at this from this direction, how does it look? So this is z and this is y, right? And this will be the infinite line charge. So this will be the infinite line charge, which is inside your screen and coming out of your screen, or perpendicular to your screen what you're watching now, right? So this y is equal to 1 and z is equal to 1. So what will be the coordinates of this for x, y, z? So it will be, x will be 0 for this because we are not considering that plane, and it will be 1 and 1, right? Now you have located infinite line charge, how it is placed based on the problem given. Now just read this one. If V is equal to 0 volt at the origin, that is 0 0 0, find V at A 5 0 1, right? 5 0 1. So now there are two things which you have to remember here. Already there are two things given. One is a point charge which has its own location, right? And we have infinite line charge which has its own location, right? Which has its own location. And rho L is also given for this line charge. Rho L is also given. Now you have to calculate the effect of these two charges at this point, that is 501. I hope you understood. First you have to calculate what is the effect of 5 nanocoulomb on this part, and then you have to calculate what is the effect of infinite line charge on this part, right? And then add those two. Now before erasing this one, this is the infinite line charge. This is the infinite line charge 0 1 1. Now we'll consider one more. We have to calculate the effect at 501. So I'll just write one more point here. It is 501. For calculating the effect of infinite line charge on this point, we should not consider this 5, because the infinite line charge is placed parallel to x-axis, so we are ignoring this point. 5. So what will be the coordinates of this point? It will be 0 0 1, 0 0 1. Now what will be the effect now? So this is the infinite line charge. I have to calculate the potential at this point due to infinite line charge, so the arrow will be like this. Now if I calculate the distance between these two, what do we get? That is final minus initial, 0 0 1 minus 0 1 1. So this will be 0 minus 0 is 0, 0 minus 1 is minus 1. So 0 minus 1 and 1 minus 1 will be 0, right? So it will be, the distance will be 1. So the distance between these 2 points will be 1, right? So this is for the infinite line charge. Whatever we have calculated now is the distance between this line and this charge. Now there is one more one more charge, point charge, which is located at 340 right? You have to calculate what is the distance between those 2 points also. Now here we'll consider that the charge is placed here -3 4 0, and here you have to calculate the effect, that is 5 0 1, right? Now this is the charge, so we are calculating the effect here, so the arrow direction will be like this. So final minus initial, so final minus initial, what it will be, 5 minus of -3 8, 0 minus 4 -4, 1 minus 0 1, right? I think this will be root of 81, so the answer for this will be 9. The answer for this will be 9. So we got the distance for these two. Now the distance between this point and the point charge is 9, and the distance between this point and the infinite line charge is 1, right? So please solve parallelly along with me so that you will understand it better, or you can pause the video and solve it and try to understand, right? Now we'll erase this. Yes. So now we'll see the formula. So as I told you, there are two charges here. One is the point charge, the other one is the line charge. So VQ will be the potential difference at 0. Anyway, it is 0 volts minus VA, that is at this point. So that is given by Q divided by 4 pi epsilon naught, 1 divided by R naught minus 1 divided by RA. So whatever we have calculated now is RA. We have to calculate what is R naught also. So what is R naught? R naught is the distance between the line charge and the origin and the point charge in the origin. So that will give you R naught and rho naught. So this is for point charge. This is for point charge, and this is for infinite line charge. Infinite line charge, you should be remembering the formula what we did, what we solved in this beginning of this lecture. So it is given by minus rho L divided by 2 pi epsilon naught ln of R naught by RA. So in that we have R naught by RA. Here we are using rho naught by rho A, right? We have already calculated rho A, which we got it as 1. Rho naught we have to calculate. So this is how we calculated RA, and R naught is like this. That is the distance between 0 0 0 and minus 340, the point where the charge is located, right? And this is rho naught. Rho naught is from the origin to the line. So line, as I told you, x we are ignoring. We are not considering x. So it will be root 2, and the other part is 1. So you got, now as I told you in the beginning, what are all unknowns here? Q we know, right? Q we know, that is 5 nanocoulomb, and rho L we know, that is 2 nanocoulomb, 2 nanocoulomb, right? Only unknown things are R naught, RA, rho naught, rho A. So that is what we have calculated here. So just substitute it. When you substitute it, this is what you get. So the potential at V naught is 0. This is given in the question. So that is why it is written as 0 minus VA. And we have to find what is the potential at VA. So when you solve this one, you get VA is equal to 8.477. 8.477. So this is the answer for this first subdivision. Now the second case, what we have to determine. Second case, yeah, same thing. There is 100 volts at B121. So this is same as this one from the previous slide. We had 0 volts at origin. Due to that you have to calculate the what is here, potential at A. Now at B there is some other potential of 100 volts. Due to that and these 2 point charges, you have to calculate what is the potential at -253. So I'll not discuss that one. I'll just show you the answer. You try to solve it by yourself, right? same thing here, right? So it will be Vc minus Vb. So there we took 0 because it was given as 0. So here Vb is taken as 100. That is the only difference. And calculating the distance is the same. Calculating the distance is the same. So try to solve it by yourself. And then the formulas are also same, right? So this is what you get. This is for Vc minus 100. We got minus 50.175. So when you take it to the other side, when you take 100 to the other side, you will get Vc as 49.825. This is the second subdivision. Now just read the third subdivision. Third subdivision, they have given V is equal to minus 5 volts at the origin. Minus 5 volts at the origin, that is 0, 0, 0. You have to find what is VBC. You have to find what is VBC. Now for calculating VBC, we know what is VB and what is VC, right? We know what is VB and what is VC. So whatever might be the charge here at the origin, that doesn't matter because we are not calculating this VBC with respect to the origin. So VBC, as it says, it is only between B and C. So it doesn't depend on any other values. So it depends only on VC and VB. So the difference of VC and VB, you get this equation, you get this answer for VBC. Just read this statement. To find the potential difference between 2 points, we do not need the potential reference if a common reference is assumed. So no need to worry about that, right? Now next, this is based on the energy density which we solved. So there are three charges. This is Q1, Q2 and Q3. So first what you are trying to do is you are trying to get Q1 to this point. So the energy will be 0. The energy or the work done will be 0. And next you are getting 4 nanocoulomb to this point. So due to this Q1, there will be some energy spent to get Q2. Now Q3 you are trying to get it to point P3. So when you are getting this, you need to consider due to this Q1 also as well as Q2 also, right? Now you just go through this equation. Now W1, so for moving minus 1 nanocoulomb to 0, 0, 0, what is the work done? It will be 0. For W2, that is for carrying Q2 to the point 0, 0, 1, the charge, the work done will be Q2 into V21. So this is the potential difference due to the first charge and the second charge which you have taken now. Now Q3, I mean W3, that is work done for moving the third charge will be Q3 into, so first charge will be already present, so V31 is required, and V32, second charge also is present, so we have to calculate what is V32 as we discussed in the derivation. Now substitution part, anyway this the first part is 0, so now here Q2 is written as it is. What is V21? V21 will be Q1 because we are moving, because this V21 is due to Q1. So Q1 divided by 4 pi epsilon naught into the distance between the first charge and the second charge. That is what is written here. Similarly, analyze this one. So Q3 is written as it is. Now V31 will be due to Q1 and this distance will be between 3 and 1. Between 3 and 1. Now what is between 3 and 1? Because that is 0, 0, 0 and 1, 0, 0. So 1, 0, 0 minus 0, 0, 0. Final minus initial. Now similarly V32. V32 will be due to Q2 and this is between the second charge and the third charge. That when you add and solve, this is the equation what you get. So and this is the work done, or this is the energy spent for 13.37, that is 13.37 nanojoule. So I hope the problem is clear. So going to the next problem, just read this problem once. So here they have given the electric field intensity. So this is not clear anyway, I'll tell you. So this is minus 8xy ax cap. So here you have ax cap. Here you have ax cap minus 4x square ay cap plus az into az volt per meter. So the charge of 6 coulomb, is to be moved from B to A. So you have to move. Now there is one point B and there is other point A, right? So you have to move this point B to A. Now how you have to move? They have given two paths. That is a curve, right? Maybe some curve like this, right? And again the second case, a straight line joining B to A. A straight line joining B to A, right? Now first case 1 will be on this curve. Case 2 will be the straight line. Now at last we have to prove that even if the charge is moved along this curve or along the straight line, the work done remains the same, right? We discussed this in the previous lecture. So whatever might be the path selected, right? The work done will be the same. Now we'll see how the problem is done. So this is the formula what we require, minus q b to a e vector dot dl vector. So now we have to see here minus q is given, that is 6 coulomb. So q is given. E vector also is given here, right? So only unknown is, or only thing what we have to check here is dl, because dl is the one which can take a curve or a straight line. So dl we have to find here. Now this is dl which is given. I mean we know that 185 and 2816, just by looking at the coordinates we know that it is Cartesian coordinate system. So E vector dot dl vector. So E vector I'm writing from the question whatever it is. That is this E vector I'm writing here. And dl vector I should know from differential lengths of Cartesian coordinate system. So this is dl. So when you find the dot product of these two, you will get 8xy dx, 4x square dy and dz, right? Now, so the work done, I'm just applying in this formula here. So W is equal to minus Q B to A E dot dl. E dot dl, I've just calculated that. I'll just substitute it here. Then here it is dx, dy and dz. Here B to A minus 8xy dx. I'm substituting only x part here, y part here and z part here, right? Z part here. Now how B to A is changing here for x? So B to A will be 1 to 2. For y it will be from 8 to 18, and for the last one for z it will be from 5 to 6, right? This variation you have to know properly. Now we'll go on to the next slide. Yes, so this is case 1. As I told you, case 1 will be an curve, right? So it is given by, the curve equation is given by y is equal to 3x square plus z, comma z is equal to x plus 4. So y is equal to 3x square plus x plus 4. Here this z is substituted for x plus 4. So when you differentiate this equation, you get 6x plus 1 into dx, that is dy by dx. When you differentiate this with respect to x, you get dy by dx, and cross multiply that, you get 6x plus 1 into dx. Now this is the equation for, yeah, this is from the previous equation, that is this one. So here For b to a minus 8 xy dx, the limits are from x is equal to 1 to 2, and for y it is y is equal to 8 to 18, and z is equal to 5 to 6. So work done will be minus q, same thing, substituting in the formula, and limits I am applying only for x, y and z, right, for E dot dl. Now here, using y is equal to 3x square plus x plus 4 and dy is equal to 6x plus 1, that is this one, this equation, and changing the limits y is equal y from 8 to 18 in terms of x from 1 to 2, we get here what we are trying to do is, here we have dy, right? I can write dy as this part, that is 6x plus 1 into dx. Now if I write this dy as this equation, the variable will become dx, right? Variable for this part will become dx. So when variable becomes dx, this y is equal to 8 to 18 will not hold good now. So I have to again substitute x is equal to 1 to 2 because this dy is in terms of dx. So that is what we have done here. You can see here the first one is also for x, the second one is also for x, just because this we have replaced for dy, right? So when you solve this, this is the equation what you get. So just go through this derivation, right? Just pause the video and you can go through this derivation. So next, case 2. Now we have finished the curve. Now case 2, how to calculate when we have 2 points, how to calculate the this thing, what is it? For the straight line, the equation of straight line is given by y minus yb is equal to ya minus yb divided by xa minus xb into x minus xb. I think everyone knows this formula. This for x, y and z. So we know what is yb, sorry, we know what is xb, xa, that is this is xb, yb, zb, xa, ya, za. So these are the 3 points which you should substitute here. When you substitute it here, you will get these 3 equations, that is these 3 equations, right? Or yeah, y minus 8 is equal to ya is 18 minus 8 divided by 2 minus 1, that is through this equation. And when you solve this equation, you get y is equal to 10x minus 2. Similarly, this equations you have to solve, and then substituting in the formula, what do we get? You can see that we'll get the same value, that is 1530 joules. So even if you move the charge in a curve or in a straight line, the work done remains the same, right? So that is the here. So case 1, when you moved this with respect to the curve, the work done was 1530 joules, and when you moved it through the straight line, it is 1530 joules. So I'll repeat once more. So if you have two charges like this, so in the presence of electric field E vector, if you are moving the charge like this from A to B, or if you are moving the charge like this, that is exactly a straight line, right? So the work done in this line or the work done in this line both remains the same in spite of the path taken. So this is very, very important, and that is why we have closed length integral of E vector dot dl vector is equal to 0. So this also, in this way also you can prove this, right? Both remains the same. So what is E vector dot dl vector is nothing but the work done, right, over a closed integral, that is this one and this one, over a closed loop, this has to be 0, right? I hope the problem is clear. So we have solved 3 problems. So this shows that irrespective of the path selected, the work done in moving the charge from B to A remains the same, right? So we'll continue in the next lecture, right? So this is the end of this module. This module will start with the next module in the next class, right? So this is one more problem I forgot to tell you. Now here we have to find E vector at this point, P00011. So they have given V. This is very easy problem. You can solve it by yourself. So you have to calculate what is E vector when the potential is given. So we know that E, that is electric field intensity, is negative gradient of V. So gradient formulas I have given you in the first module when we discussed in the class. So just apply those formulas here with a negative sign. Don't forget to put this negative sign because it is a negative gradient. So you have to just find dou by dou x. You know better than me, that is differentiation. So you have to just find the differentiation and get the answer. Now here only thing what is different is here P011 is nothing but these coordinates are in Cartesian coordinate system, but here they have given it in spherical coordinate system. So before solving or applying this one, what you have to do is you have to convert this xyz to r theta phi. You have to convert this to r theta phi because the second problem, this problem is spherical coordinate system. So for that you can use this formula. Here xyz is converted to r, phi and theta. So applying that you will get what is E vector at that point, right? Thank you. So now here, yeah, this is we have discussed everything here. You can go through this one. So this was already discussed in the class. So potential difference, potential gradient, energy in electrostatic field and energy density. So this one we have discussed now. So from the next class, we'll start with electrostatic, boundary value, problems and conductors, right? Thank you.